As I mentioned before, in the next couple of videos, we will elaborate lattice structure from hyperelliptic function fields, and particularly we will be focusing on the well-roundedness property for these function fields. And I mean, I will follow this research paper written by Lattices and Henning Stettenat. He was also the author of the textbook we followed in this lecture. But instead of like opposite to the lattice structure coming from rational function fields and the elliptic function fields, we will see that they are working with different tools to conclude that lattices from hyperelliptic function fields are not well-rounded. So that means they are not going to investigate like the spatial choice of the rational places or investigating the OP star. That was the case for the rational and the elliptic function field. They will work with the general tools, and they made an effort to see how can we see that the hyperelliptic function fields, the hyperelliptic function field lattices are not well-rounded. First, recall that we define the hyperelliptic function field actually over any field K as genus at least zero, is genus at least two function field, and there exists a rational subfield of extension degree 2. This gives us the gonality of the hyperelliptic function field should be 2. And similarly to the elliptic function fields, we have seen that it can be also described in terms of an algebraic relation where f of x is degree 2g plus 1 or 2g plus 2 carefree polynomial. And we also have the other way around, but that wasn't so that easy to derive this relation. But we should be careful that, I mean, in my opinion, they are not generalization of the elliptic function fields because their structure behave differently. For instance, for the elliptic case, if they have elliptic function fields, number of the rational subfields whose extension degree is exactly the gonality. So 2 is exactly determined by the number of the rational places. But in the hyperelliptic case, we always have unique rational subfield with extension degree 2. It's coming from the Riemann's inequality by studying with the genus. So in this sense, they are not the same, but this fact will be important today. And for the gonality, let me also mention that we define it as the minimum extension degree f over a rational subfield. By the rational subfield, what we mean is the rational function field. In that we can relate this invariant to genus, like g plus 1 is always bigger than the equality of the gonality. And I highly recommend you how to say this equality. This is the consequence of the Riemann-Roch theorem. And here you may approach by considering the rational subfield, which gives us the extension degree exactly as the gonality. And we know that this extension degree is the degree of the pole divisor of this transcendental Z. And just apply the definition of the genus, which is given in terms of the degree and the dimension of the all divisors. So that means for any divisor, and particularly for Z infinity, genus will be bigger than equal to plus 1. And by analyzing the dimension of the pole divisor of Z, you may derive this equality. This is a nice exercise. And secondly, we can also relate the gonality with the number of rational places for a function field f over q. We know that this is going to be finite. And indeed, we can see this inequality like by considering the material from the last week, because we know that the rational function field over FQ has Q plus 1 many rational places, because its rational places will be determined by linear polynomials Z minus alpha, where alpha is element in the finite field. So in total, we have Q many rational places in this form, but we also have P infinity. In total, we have Q plus 1 many rational places. And for each rational places, we know that we can have at most extension degree many extensions of the places of this each place. So this is coming from like consequence of the fundamental equality. So that means the total number of the rational places in an elliptic function field should be bounded above, let's say, if this is the gonality, gonality times the number of the rational places. So this is why we have this inequality. And let me also remind you some fact from yesterday. For the lattice construction, if we in general, by the way, these are these verbs in general. Again, when we recall the lattice construction from any algebraic function field, we have concluded that its minimum distance is bounded below the square root of 2 times its gonality. And we have seen that equality holds if and only if there exists a rational subfield E of extension degree exactly the gonality and at least 2 rational places of E splits completely. Split completely in the extension F. So by the split completely, what we mean is that if we have E here, if we have F here, this is rational, and if you consider the 2 places, the number of the extension places of P1 and P2 should be exactly the same with the extension degree. Pn1 and P12 and Pn2. So indeed, what they look at to analyze, like, do we have this property and the function field satisfies, like function field lattices satisfy the well-rounded or not, or can we give a characterization by using this invariance or this proposition. So before that, let me present a proposition 2.2 from this research paper, which tells us if we consider a rational subfield of F with extension degree is exactly the gonality, and suppose that, like regarding this previous observation, suppose that there exists at least 2 rational places of E which split completely in the extension field. And we know that in this case, the minimum distance is going to be square root of 2 times the gonality. But for the well-roundedness, what we want to consider is the set of minimal vectors, right? And we want to check that if it contains exactly rank many linearly independent vectors. By the way, these linearly independent vectors are not supposed to be the basis for the lattices. So this is this kind of counterintuitive when we consider the vector space structure over a field. We should be careful about it. And if this is the case, indeed, we can count the number of S of E. So that means S of E, the set of minimal vectors, contains m times n minus 1 times q minus 1 minimal vectors. So here m is the number of rational places which splits in the extension. And the vectors like the images of the vectors in S of E span a sublattice of our function field lattice of rank m minus 1. Again, m is the number of the places which splits in the extension. And to be able to see that, first we consider the fixed notation for the rational places which split completely in F. And we can observe that the elements in the set of minimal vectors are exactly the elements in E whose principal divisor in E has in the form of Qi minus Qj for I, j runs through 1 and m. And since they are principal, we want to mention that they are not zero divisor. And here, by this notation, what we mean is the principal divisor in the rational function field E. And we've also elaborated differences of the principal divisor of set in the function field F, but it was determined, completely determined by this principal divisor, thanks to Conon. And indeed, just by doing the counting argument, like how many principles do we have in this form, exactly we have m times m minus 1 many places, choice of the places is possible. So that means we have m times m minus 1 many such divisors. And each of them are q minus 1 elements z in F. So like we have actually this q minus 1 like coming from the as an extension. So that means number of S of E is exactly m times m minus 1 q times 1. And for the second part, first we fix elements. Let me denote it by Zij in E with principal divisors in E in the form of Qi minus Qj. Now for any ij, to up to m, different, like with the different indices, Qi minus Qj indeed can be written the principal divisor, like with respect to this notation, we can write this equality as a principal divisor of the function z sub I1 and principal divisor of the function zji. Then their images under phi since they are rational, is going to be the difference z minus I minus phi of z j1. We can also observe that the image of the function z1j is going to be like containing 1 and minus 1 is exactly minus phi of zj1 because zj1 is qj minus qi, so we are multiplying this vector by minus 1. And indeed, this shows us the vectors which is determined as the image of zj1 generate the lattice and which is spanned by all phi z in SE. And when you verify that when you verify the linearly independence of these lattice vectors, then you can see that the rank should be m minus 1. And for like one addition, it cannot be m. So that means if you consider the additional element, it should be in the linear combination of these elements. And indeed, this is the fact explained here. And now we want to investigate, like we have a sublattice and we have the function field lattice. And the second theorem will be about what we can conclude about their rank. And I will explain it in the next video.